Hello everyone, I'm Tianyu, and today I want to talk about our work on supporting fast transactional workloads on universal columnar data formats, namely Arrow. Before we get into the rest of the talk, meet Joy, a data scientist at a promising new startup. Joy wants to do some analytics on his application data from an OLTP system. The other thing about Joy, he's also really not known for his patience. Now, how would Joy go about doing this? In an ideal world, an omnipotent DBMS sits at the center of the universe. Applications issue transactions to the database, Joy asks his questions to the database in SQL, his questions get answered, everyone is happy. Joy is not convinced though. Here there's this thing called Python and every data scientist is supposed to use it. Any chance you guys can support that? Well, that's easy enough, right? Just take the data out of the database and do whatever you want with it in your Python tool. There's just one problem though. The bandwidth from a DBMS to an external tool is very low, as you can see from this very thin arrow over here. Our current protocols are really designed to send small answers, not load large corpus of data elsewhere. Overall, we get terrible data transfer rate with this approach. Let's try this out and see how bad it actually is. Here we're loading around 8 gigabytes of data from Postgres into Pandas. That's not a lot of data, and in theory we should be able to do it very quickly. Copying 8 gigabytes of data in memory only takes a few seconds, and if you export your data out into a CSV file and read it back into Pandas, this will take a couple of minutes. If you use a database connector like ODBC, however, it becomes unbearably slow. Switching to a proprietary network protocol doesn't really help. So what do? In practice, many organizations have to separate their data storage into a dedicated OLTP front end that processes transactions and periodically prepare the data downstream for analytics. This process is usually called extract, transform, and load. This backend data warehouse can then much more efficiently interface with whatever analytical tools you have and get answers to Joy. Did we say Joy is not patient? Well, Joy is currently not very happy because he must wait until the next time the two systems synchronize before he can look at the latest data. He wants those answers now, not tomorrow. Frustrated, Joy continues with his hot take about the current state of the data pipeline. He says that we're doing all this extra work for reasons he can't really understand. After all, the data is right there in the database, right? Like, if he can run SQL queries against the data immediately, why can't he do the same with Python? Well, slow down there, Joy. Any database class will tell you that OLTP and OLAP are two different workloads, and we need specialized data formats for each. If you do that, you'll have to transform and load data between different formats before you can use them, right? But of course, this begs the question, what happens if we don't use specialized data formats and instead just pick one for both workloads? Does Joy's problem now go away? And is that really so much performance overhead that we should really ignore the benefits it might bring? Restating that in a more concise question, can you efficiently run both transactions and analytics on one storage format? If you can, then maybe Joy doesn't have to wait until tomorrow after all. Let's think about that for a bit more. This idea of a universal format is not new. I don't really have to convince this audience that Arrow fits the bill for a standardized format on the analytics side at least. That's half the solution right there to the universal storage format question. The other half that remains is whether we can run OLTP workloads efficiently on Arrow. The answer to that question turns out to be a yes, and that's what I'm going to talk about today. For the remainder of today's talk, we'll first look at what makes Arrow supposedly difficult to use for transactions. We'll then discuss in detail our technique for running transactions on Arrow. And lastly, we'll showcase the performance of our system and the benefits downstream applications might enjoy from this architecture, and some lessons learned for future systems. As you all know, Arrow is designed with performance and generality in mind for a variety of analytical workloads, owing to its lightweight, succinct columnar representation of data. However, conventional wisdom would suggest that these positive traits of Arrow also make it unsuited for write-heavy workloads, and the key issue here is write amplification. Here's a concrete example of what I mean by that. Suppose we have a table like this with one ID column of integers and one name column of strings. Arrow first uses a metadata header to encode the schema like this. Of the two columns, the integer column is considered primitive, and we can just represent it with a contiguous buffer of 4-byte integers. The string column, on the other hand, is represented by a buffer of characters and an array of offsets like this. For example, we know the first string is Joe because that's the array slice between 0 and 3 in the offset array. This is a very efficient representation if you're scanning through a table. However, there are two major problems with it if you're to modify the data. First, let's take a look at deletion. Here we're deleting the second row in the left-hand side table. This creates a hole in the buffer, and because Arrow keeps everything contiguous in memory, we have no way of denoting the absence of a tuple. We have to instead shift everything up, which could be a lot of work if you have a large data frame. Another problem is when we're trying to update variable length values. Here, we're trying to update ID 102 to have the name Anna. We first run out of space in the Arrow character buffer, add to shift everything down to accommodate, potentially allocating a new buffer entirely. We then need to update the offsets array to point to the new positions in the character buffer. This is again O of n in the worst case with regards to data frame size. By now it is clear that this type of write amplification is the key obstacle to running transactions on Arrow. Our solution relies on a key assumption in OLTP workloads, that most of the writes happen to a small hot portion of the database, and the hot data cools down to become more read-heavy over time. This allows us to keep Arrow data in a write-efficient representation when it's hot. As the data cools down, we can then transform it into the read-optimized Arrow format. You might ask, what exactly is new with this approach? Why is it different from before? The ETL processes also periodically moving data from write-optimized to read-optimized formats, right? Well, first and foremost, we explicitly do not have hybrid storage like that. Our transaction representation is basically still Arrow, but with some extra columns and accessed differently. This allows the transformation to be much quicker, on the order of milliseconds, rather than minutes or hours. Because of this, we are able to piggyback this transformation onto the normal garbage collection and memory compaction procedure necessary for any OLTP system, which minimizes the runtime overhead. I'll talk about these ideas in detail next. Let's now look at our transactional Arrow format. On the right, you can see the read-optimized table from before. These are the Arrow buffer readers expect, and we cannot make much modifications to it. Therefore, we instead allocate these two new columns for transactional information. The first one is a bit vector of whether a tuple is present, used for deletion. That's pretty self-explanatory. For variable length updates, things are slightly more complicated. We allocate an additional 16 bytes for each row. 4 bytes of size information, 4 bytes of prefix, and an 8-byte physical pointer to the varlen value in memory. We use the combined 12 bytes to inline short values, like Joe over there. For illustration purposes, we're storing Marco using the pointer. Here's the same delete workflow from before. To delete tuples, we simply flip their presence bit in the transactional column. All transactions access tuples through this metadata, so they'll observe this change. Readers that are currently looking at Arrow data, however, will miss this update. We'll talk about how we reconcile that difference later, but as you can see here, the deletion operation involves no write amplification. Now to look at varlen updates. Similar to deletes, the trick here is to only make changes to the transactional metadata without touching the underlying Arrow storage. Here, we're trying to insert this string data thread into this table. We can just allocate the string out of line and swing the metadata pointer to it. Again, no write amplification. To get a fully functional transaction engine out of this idea, we allocate one last extra column for use as a version vector. This holds a physical pointer to the start of a version chain. We can then use the tried and true multi-version OCC protocol to implement transactions. A transactional worker would add a delta to the version chain and then modify values in place. For deletes and varlen updates, this goes to the transactional metadatas. For fixed length values, we allow them to directly update the Arrow buffers. The transactional protocol is quite straightforward. A centralized transaction manager issues serial timestamps used to determine the ordering of transactions and what each transaction can see. Essentially, a transaction gets a timestamp at its start, which determines the snapshot it sees. As the transaction writes to the table, it generates delta records, which is stored in the reusable context objects, separate from Arrow storage. This will simplify garbage collection down the line. Eventually, when a transaction commits, it gets an end timestamp, which determines the point at which its writes become visible to others. To To correctly maintain multi-versioning, transactions first copy the current image of a tuple into a delta record and atomically installs that onto the version chain. A negative timestamp here indicates that this is an uncommitted version that nobody else should see. For simplicity, we disallow conflicting updates, and transactions simply abort if there's already an uncommitted delta at the head of the version chain. After the delta is installed, the transaction is safe to update the table in place, as other concurrent transactions will instead attempt to recreate the tuple from delta records. Eventually, the transaction commits, and we change the timestamp on the delta record to its commit time. Let's take a step back and see what this gets us. We can divide our data into a number of chunks called blocks. On the left side, we have the hot portion of our database. Much of the data is already in Arrow, but information is still scattered across delta records and transactional metadata columns. Readers need to traverse the version chain and reconstruct tuples. On the right-hand side, we have the code portion of the database. These tuples are not actively updated, and all data is available in Arrow. Readers can directly scan as they would any Arrow data. As we have mentioned before, we will go from left to right through GC and compaction. This is where we reconstruct Arrow columns using the information we have been accumulating in transactional metadata columns. The other direction, meanwhile, requires no transformation. Writers can just add a delta to make a block hot again. The only thing they need to do is to make sure they are not interrupting concurrent in-place readers. Let's talk a little bit more about how we transform blocks into Arrow. Users work on hot blocks exclusively through transactions. And as we have stated before, we need a garbage collector to prune outdated version chain and reclaim transaction context as they're done. This naturally gives us access statistics, as the GC will see all recent updates and can just stream this information to an access monitor. The access monitor detects when a block is no longer being updated and sends it to the transformation pipeline to be worked on. We first need to fill in any gap resulting from deletion. We call this compaction. We group some blocks together and use a transaction to shuffle tuples within them to make them contiguous. At the end of compaction, there are no holes within blocks, and GC can reclaim any freed space. We need to do this anyways for long-running systems. At this point, the block is considered to be cooling, but not quite cold yet. Eventually, the cooling block is flagged again, and we'll send it to the formatting phase, where we gather all previously out-of-line varlen values into contiguous arrow buffers. You can also run compression as part of this process. At the end of the stage, we have full arrow blocks that Joy can look at directly. As a byproduct of moving varlen values into contiguous buffers, we're also reducing memory fragmentation with our system, which is often a good thing to do anyways. This is by no means an exhaustive presentation of the technical challenges involved in our solution. Ensuring that the whole pipeline is thread safe without introducing new bottlenecks for transactions is very tricky. We cover this topic in much more details in the papers. In fact, we're able to generalize some of our techniques into more papers. Please check all of these out if you're interested in the details. We will now show some of our results. We implemented our scheme in CMU's NoisePage system and ran the tried and true TBCC benchmark on it. All transactions execute as stored procedures, and we report overall transaction throughput. We can see that NoisePage loses just below 10% performance when we turn on this transformation feature, proving that the transformation is very lightweight. In realistic scenarios, where transactions are coming in through the network, this overhead is often negligible. Let's take a closer look at the transformation algorithm itself. Here, we plot NoisePage's runtime behavior through 5 minutes of TBCC with transformation turned on. The blue line shows the backlog of data that needs to be transformed in megabytes, and the red line shows transactional throughput. We can see here that the transformation process can easily keep up with the high throughput and periodically clear its backlog. Transaction throughput is steady throughout despite the background processing. Overall, our effective transformation comes to about 1 GB per second per thread without any additional compression. This shows that our transformation is extremely lightweight compared to the nightly ETL pipeline. Cool! All this transaction talk is fine and exciting, but what does this have anything to do with our friend Joy here? Well, for starters, let's go back to our original use case, where Joy wants to do a select star over his OLTP system. With NoisePage, the vast majority of OLTP data is already available in a format understandable by Python, so we can skip the whole wire protocol and query thing and just dump raw bytes onto the wire for Joy. For the small hot portion, we'll have to transactionally materialize a snapshot and send that to Joy, but hopefully that won't be as expensive since the amount of hot data will be small. We ran an experiment for this use case, loading about 7 GB worth of TPCC data directly into pandas. For this experiment, we mark 80% of the database as cold and fully transformed. For the cold portion of the database, there are a couple of things we can do here. One, we can leverage the Arrow ecosystem and use the zero-copy RPC library, that is Arrowflight, to send the data. Or two, because we're just doing raw byte copy, you just use RDMA to quickly send the data directly onto the client's wire. We compare this against two baselines. One is sending data over the PostgreSQL wire protocol, and the other is to send it with an improved wire protocol, as proposed by this particular paper. We implement both protocols on top of the NoisePage system according to their specification. Here's what we get. With Arrow storage, NoisePage is able to almost saturate the 10 gigabit network that we tested it on. Arrowflight in particular is, surprisingly, able to achieve performance close to RDMA thanks to Arrow native storage. The two wire protocols, on the other hand, are not doing so well. We also run the same benchmark with 100% of blocks hot in NoisePage. This effectively disables native Arrow storage and forces all data to be copied, transformed, and serialized onto the wire. We can see here that in this case, Arrowflight and RDMA both regresses to the performance of the improved wire protocol. This serves to show that the previous speedup results not just from a better implementation of communication protocols, there really is something fundamental about having your data in native Arrow that leads to much higher performance when exporting. This is just a small example of what universal storage can do for us in the data processing pipeline. Looking ahead, we can try to add more functionality to NoisePage's transformation process and introduce features such as filtering or aggregation, essentially pushing more of the ETL pipeline up into the OLTP system. Or perhaps more interestingly, because NoisePage has Arrow data natively, Arrow can serve as an API between the database and external tools. Because much of the data science world is programmed to work on Arrow, in theory, any of them can execute directly as a UDF on NoisePage, because NoisePage's data is mostly the same in the same format. This opens up some exciting opportunities for compute shipping architectures, in addition to just data shipping ones, like the ones we've shown before. To summarize, we have shown in our prototype system that Arrow can support high-performance in-memory transactions with the appropriate techniques. Specifically, our implementation optimizes for OLTP, which let us trade off some space efficiency by allocating extra Arrow columns to hold transactional metadata. But we don't see that as fundamental to our approach. The same insight might still apply when optimizing your transactional Arrow implementation for something else, say large write sets and storage efficiency, like Delta Lake. We have hopefully shown that having native Arrow storage can bring much benefit and speedups across your entire data pipeline. All things said, in 2022, you should definitely build your new system with native Arrow storage. It is doable even for the seemingly undoable cases and can get you much benefit down the line. At the end of this talk, I would like to give a shout out to my collaborators on this project. You can find our project website in the link here. The NoisePage prototype is open source on GitHub. If you have any questions or comments about this work, please do not hesitate to send me an email. Thank you very much.